All right, guys, I want to do some examples, some geometric sequence examples. Kind of show you maybe some different notation that might be used periodically. And then we'll move on towards the end of the period, talk about an annuity formula. All right, so I want to give you, let's go with do the one we did yet or last period. 1 plus 3 plus 9 plus ellipses 2187. And I asked you to sum this. Now it's because of the replacing of commas with plus signs, it's now not a sequence, but it's called a series, right? But a series is generated just from that sequence, okay? We just put plus signs in there. Or, you know, if my sequence is generated like alternating plus minus for the terms, then we'll have to throw plus signs in. The plus minus is actually negative, right? Or a minus. So this could be a plus sign, minus, plus, minus, plus. Could be minus, plus, could be all pluses. It's just depending on what your rule is that's generating your sequence. So when I want to add these up, okay, this is a finite series, meaning this term here is maybe the 12th term or the 15th term or whatever. I know or I have the ability of finding how many objects are in this series. Does that make sense? Okay. Now if I want to sum a geometric sequence or series, yesterday we talked about the fact that S sub n, okay, S sub n is going to be, this is of a finite list, it's going to be A sub 1 times, now the numerator is 1 minus R to the n over 1 minus R. Okay. When you're typing this on your calculator, my suggestion is to make sure that you put parentheses there, in there. You're going to type it all in at one time. And then that will make sure that this A sub 1 gets distributed to the numerator correctly. So, kind of filling in from our information here, I don't know how many things are in that list, right? So when I ask to find S sub n, I don't know what n is. I don't know how many objects I'm actually adding together. But we do know that A1 is 1. We should know that we have 1 minus, what is our R value here? 3, okay? And I think the best thing to do, guys, is to take 3, take your second term, divide it by your first term. That gives you a thought of what R should be, right? Then see if applying that R to the second term generates the third one. Then see if that generates the fourth one and the fifth one, however many things you have in your list. Okay? 3 does that, right? Okay, so R is 3. But again, I don't know what n is. So I start filling in these things, and I'm left with that equation, meaning I've got one variable, I've got to find what n is, right? So this series gives me a way of finding n if I understand or know what the rule is that generates that series. Every rule that we deal with that is geometric is of this form, right? Would you agree with that? Every geometric sequence is of that form. So this 1, the 3, the 9, the 2187 are generated by some unknown rule. Okay? Well, that rule is pretty easy to find. A sub n is equal to A1 times R. You said R was 3, right? To the n minus 1. Well, that's just A sub n equal to 3 to the n minus 1, right? Okay? Now understand what this a sub n, hopefully we know this, but this has been one of the biggest things throughout all the years I've taught this that people get kind of confused with. Remember, n is the position of these objects in the list. Okay, we don't know what this 2187 is, right? But 1, that object, the actual object in that position, is an a sub n, right? 3 is an a sub n. It's specifically a sub 2, but it's some a sub n. Same thing here, right? So this is some a sub n. So these were, that's a1, a2, a3. I don't know what that n is, but I know that whatever it is in its spot is 2187, correct? So can I put 2187 right there? So 2187 is equal to 3 raised to the n minus 1. Does that give you an exponential equation? How do I solve exponential equations in which the variable is in the exponent? I use logarithms, okay? So I'm going to take the natural log, and that's the easiest thing. So ln this side, ln that side, so it gives me ln of 2187. When I ln the right-hand side, obviously I get ln of 3, but the n minus 1 comes out as a coefficient now, right? All right, so a couple things at this stage. I think there's a couple things to talk about, and they go hand in hand. Because I'm looking for n is a position in a list, right? I can only have integer positions, all right? I guess natural number positions: 1, 2, 3, 4, 5, 6. I can't have 2.5. I can't have 3.7465. Okay, I cannot have those non-natural number values when I solve for n here. So when I divide that every single time, I should get a whole number on the left-hand side. Does that make sense? It should be positive. If not, you've done something wrong throughout the algebra. The kind of second thing to realize, and it plays into that as well, is think about each of those positions. 9 is a multiple of 3, right? It's 3 squared. Okay, the next number is going to be 27. That's 3 cubed, right? The next one's going to be 81. That's 3 to the 4th, right? Okay, so I should be getting essentially, when I take ln of 2187 divided by ln of 3, that is going to give me some power that I raised 3 to get that 2187. Does that make sense? So when I go ahead and solve, so what's that give you? Does it give you 6 or 7? This gives you 7, so I get 7 is equal to n minus 1. Okay, so then n would be what? N would be 8, right? So 2187 is in the 8th position. But if I think, just kind of going off of what we just mentioned, that just gave me, when I go 3 raised to the 7th, does that give me that 2187? Does that kind of make sense? So the the ln of 2187 over the ln of 3 is generating that power for me. But I didn't want 7. I didn't want the power that I raised 2187 to. I wanted to find the position of 2187, right? Because that's what's in my formula here. So now can I take that n and make it 8 right there? All right. So then doing that, grab calculator. I'm going to type in 1 times, was it 1 minus r to the 8th? And we'll divide that then by 1 minus r. And we see that we get 3280. 3280 as the sum of those first 8 objects in that list. Is that okay? I showed you guys this yesterday, but I just kind of want to go through this again because I think it is beneficial for us all to see one more time. All I've done here with Excel is taken taking our R value, so if I take my R value, what was it, 3? Okay. My A sub 1 over here was 1. And then if I just click on that there, it shows you this rule up here. And basically all it's doing is saying, if you can, I know it's kind of zoomed out, it's kind of hard to see, but it says E2, and it's got the money signs around E, but it's just forcing Excel to always go back to what I have in that blue cell, essentially. So it's taking A sub 1, which is 1, multiply it by A2, which is the red cell. So I take 1 times 3. And then it says raise that to B2 minus 1. Well, B2 is that small blue cell in B2, which is a 1, right? So it's raising our 3 to 1 minus 1, which should just be 0, correct? And it's going to generate our value for that first position. Now, if I look at this one, oops, I always do that. All right, look at that one. Now you see that the B2 turned into a B3. So it's allowing me to change the position, right? It allows it to, we call it like an index or a counter that allows you to transition to the next spot in your list, okay? Everything else was the same, right? The E2 was still 1, so A sub 1 is still 1. My R value is still position or cell A2, which is still 3. But now my N minus 1 is now 2 minus 1. So that's going to give me the second value. And I keep doing that. And you see here that these numbers, we go 1, 3, 9, 27, 81, 243, 729. So these are just your powers of 3, right? Okay. What are those numbers doing as they successfully move along that list? Yeah, they're getting bigger and bigger, right? Okay. So here's my question. What do you get if you start adding all those up? Yeah, I mean, if you're adding things that are very, eventually offending themselves, when I add those up, we're going to get a number that is not known. Does that make sense? Okay. And we're going to get infinity as well. So what we say with that kind of stuff, when we start adding this type of series together, you guys remember the word that we used yesterday about this thing? It's divergent. Okay. This thing does not kind of settle in on one value when I add them all together. Okay? And that should make sense because didn't we say yesterday for something to be divergent, the absolute value of R had to be less than 1, meaning that R had to be between those two values. And right now we're seeing that R is outside that, right? So we make the argument before even having to do any calculations, before seeing anything in this list, we absolutely know it's divergent because that's going to always force these numbers, when R is greater than 1, that's the value is greater than 1. So we always force these values to increase successively. Okay. So let's talk about one. It's a little bit different. Yeah.
I just had a question. So the way that I did this, I don't know, kind of cheatily different. So we don't really care what n is. We only care what 3 to the n is, which you will always get when you apply your rule to the last term that you know and get the next term, right?
Say.
So if we have, what was it, 2187?
Yeah.
Right? And we know now that's 3 to the 7. But we didn't know. We knew that was 3 to the n minus 1. And we were looking for 3 to the n. So if we do 3 to the n plus 1 minus 1, don't we just get 3 to the n, right?
Yeah.
So if we just find the next term in the sequence after 2187.
So you're saying multiply this by...
Yeah, so just take the next term because we know what our, what do you call that in geometric sequences? It's not common difference, it's
The common ratio?
Common ratio. So we know what our common ratio is. So if we just, find the next term and then just plug that in.
So you have 2187, and then you'll have 6561. That's the next term, right?
Yeah.
So you're now saying that is...
That's 3 to the n.
This is 3 to the n.
Yes. In relative terms to that being 3 to the n minus 1. And what we're finding, that is 3 again.
Yes.
So can't we just take that? So we do 1 times 1 minus 65, 61 over 1 minus 3.
Yes. 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 That'll work every time. Yep. That's good logic. It's going to be hard. I'm not going to be able to explain that again, but if that's the route that you want to go, then by all means do that. That will work. Okay. I think that's actually pretty ingenious, because what he's saying, guys, is that in our formula, we want 1 minus r to the n, right? Okay. Well, if I think about r to the n, like he's saying, that is the next term, right? Okay. So if this is the final term in our list, r to the n, this is the n minus 1, this would be r to the n. So he's saying figure out whatever that number is, plug that number in right here, and go 1 minus that over 1 minus r. Okay, and that will work. That's fine. Let's talk. Let's do. Oops, wrong thing. Let's do this one. Where did it go? Okay, so we got 2/5 plus 4/25 plus 8 1/25 plus dot, dot, dot. Okay, now in the last one, after those ellipses, we had a final value, right? We had an nth term, so we knew that the objects that we were providing our list were countable. Okay? You could say we got 6 in our list, or 7 in our list, or 8 things in our list. Here, those ellipses don't have anything after them, right? So what's that telling me that this list is? Infinite. This list is uncountable. But they still want me to add it together. Okay? So what we do here is we realize that this is an infinite. I'm going to say, in a moment, we're going to put geometric right there. Series. Okay? The reason we know it's geometric, what would be the common ratio between that one and that one? Four 25ths divided by 2/5, right? Two-fifths, isn't it? Okay, so my common ratio is 2/5. If I take this 2/5 and multiply it by 2/5, do you get that? Multiply this one by 2/5, do you get that one? Yeah, okay. So R, my common ratio is 2/5. Okay, so it tells me it's geometric. Okay, now my question is, how do I add up all these infinite things? If I don't have an understanding or an ability to actually write down every single one, how do I sum them? Okay, well, we understand that, and we go through, you find the proof that explains this, or generate the proof that explains this, why this makes sense. If I'm going to sum an infinite geometric series in which our R value is less than 1, is that what we got here? Okay, so our R value is less, the absolute value of our R value is less than 1. So that means that the sum of the entire series, an infinite number of objects. Now, you don't usually write the subscript of infinity there, but we're going to add up an infinite number of things. Okay? Now, we talked about this yesterday. Some people are going to argue, well, if I'm adding an infinite number of things, then I'm going to get infinity, right? Not if those infinite number of things start getting smaller and smaller and smaller and smaller, right? Is this list itself, are the successive terms approaching 0? Yeah. Okay? So then when I start adding those up, when I'm all the way down here at the, maybe 100 millionth term, there are so many zeros there before I start seeing my non-zero numbers or my non-zero decimal places. that it's a very minute, negligible amount. Does that make sense? Okay. So when we're adding up an infinite number of objects, the formula to that, the sum, is very straightforward. It's very easy. A sub 1 over 1 minus r. Okay, so a sub 1 for us is 2/5, right? 2/5 over 1 minus 2/5. So it gives me 2/5 over 3/5, right? Hopefully you guys remember, if we have a fraction divided by a fraction, they both have the same denominator. When I do the reciprocal and multiply, all I'm going to be left with is the two terms that are not the same. In that order, I'll be left with 2/3. That's just kind of a shortcut. So that sum should add up to 0.6 repeating. Okay, now if I were to just kind of go back to Excel real quick, and I think we did this one yet, or something like this yesterday, but my R is 2/5. Okay, so 0.4. My first term, likewise, is 2/5, or February 5th. That's the one thing I hate about Excel, is that it defaults the cells to non-number cells when you type in fractions. So you got to change that to understand what a fraction means. So 2/5, there's our 0.4. All right, so looking at our list, so 2 over 5 is 0.4. 4 over 25 is 0.16. 8 over 125 is 0.064. If you start looking at these, what happens, the further and further that we go down in our list, I'm going to trace these out the best I can. You start to see kind of that triangle of zeros, right? Does that make sense? And that's going to that pattern is going to continue. These zeros are coming down here now, right? So if you were to add these things straight down, add these cells straight down, okay, is the sum, let's just look at, those. If I were to add those straight down, are they going to impact those zeros out there? Of the other things that are being added straight down? No, okay? If we just, kind of investigate this a little bit, let's go equals the sum. Let's just go C2 to C10. So add the first, what we got, 9 objects there. Add those together. I get 0.6664919, right? If I add C2 to, let's say, C15. Okay? Now, that 4 right there where my cursor is has now become a 6 right there, right? The 9 after it also became a 6, correct? Now when I go sum of C2 to C, let's just go 18, just a few more. We see that that 4 right there in the previous sum now turned into a 6, right? So as I'm adding successive terms that are smaller and smaller, do we see that it's going to take these non-6 values and eventually generate them and turn them into 6? And it's going to continue to do that throughout the entire list. So when I ask it to find the sum of C2 through C100, we see that it's going to add up, and it's going to make that number a 6, right? So if I go to C, like 200, I'll have more 6s out here. Does that make sense? Now, 200 is not anywhere close to an infinite number of objects, right? But we're starting to get a projection here that we're seeing that we're going to arrive at that 2/3 sum, even though I'm adding more and more and more objects, okay? Because it's going to change these decimal places. So the 201st term has no impact on that 6 right there, no impact on that one, and so forth. Okay? So that's kind of a logic of why adding an infinite number of things, if those things are getting smaller and smaller, why we get one concrete value and not infinity. When you see this on the final exam, they're not going to provide you the list this way. Okay? That list, is that generated by some a sub n equaling a sub 1 r to the n minus 1? It's geometric, right? So a sub n for us in this list would be 2/5 times r, which is 2/5 to the n minus 1, right? That makes sense? Okay. Now, instead of, so that is the rule that generates every one of those things, right? Okay, so a better way of saying, because right here, if I give you this list in blue, I have to tell you in English then, find the sum of that infinite series, right? Okay. However, if I give you the rule down here, if I give you this, all I have to do to direct you on what I need you to do or what I'm asking you to find is to write this. Does that make sense? Okay? Because that sigma notation tells me find the sum, right? Starting at the first object, n equaling 1, start at the first object. The upper bound is infinity, right? So it's saying you're adding an infinite number of objects together. Okay? If I look at this, this is my a sub 1, this is r to the n minus 1. It's geometric, right? So if I can recognize this, that this is geometric, your r value is between -1 and 1, or the absolute value is less than 1, you can now know, well, that is going to equate to a sub 1 over 1 minus r. A sub 1 is at 2/5. R is that 2/5. You plug that stuff in, and you move on to the next. Is it okay? They give it that way. I think it's more concise, but I think at the same time that when you develop that conciseness, that saying a lot with as little as possible, you lose kind of maybe understanding as a reader or an audience. Does that make sense? Okay. Obviously, if I gave you 2/5 plus 4/25 plus 8 1/25, I say find the sum of this infinite geometric series. There's a lot of information in that. If I just give you that and say find sigma of n equaling 1 to infinity of this thing, is that obvious that we got a geometric sequence? Turns into a geometric series when we sum them together, and it's convergent. Does that make sense? So you're going to see something like that. Let's see. Does anybody have questions on? So we're practicing the geometric approach here. But if you were to look at question 7 from the practice exam I gave you, okay? Does this look eerily similar to what we just did? All right, but look back to successive terms. Am I multiplying to get the next term? No, it's not geometric, right? It's arithmetic. But it's the same process, okay? Instead of using a sub n equals a sub 1 times r to the n minus 1, I'm now going to use this formula. That's my arithmetic formula, right? Okay. A sub 1 is 14.5. There's n minus 1. Common difference is 3.5. Okay. Well, if I want to find the sum of the first n objects, okay, the sum of the first n objects, I don't know what object 221 is. I do not know what position that is in my list. So coming down here, these are my two formulas for summations of arithmetic sequences. They involve a sub 1 and they involve a sub n or n. Okay, however you want to view it. Okay, and really using that one or that one, there's no better one to use because don't they both have in them? That makes sense? Okay. So I need to find n. I do not want you to sit, and tomorrow I give you a question that this is not going to be possible for you because it's going to be very time consuming. I do not want you to sit with 14.5 and push plus 3.5, and then push plus 3.5, and then push plus 3.5, all the way up to 221 to get how many objects are in that list. Does that make sense? If you would have done that here, you see the work that I did. So I say 221 is generated by 14.5 plus n minus 1 times 3.5. You should be able to solve that, get n to be 60, right? So you would have done that 60 times before you got to 221. And then you got to go back and count how many times you did that, right? Chances are you're going to mess that up. Okay? Tomorrow, when that number is larger than 60, it's even more tedious. Okay? So don't use the trial and error process. Use the algebra. Okay? So this is kind of working through an arithmetic sequence, an arithmetic sum, but you use the same logic as you do it with a geometric, right? Okay. I want to talk about an annuity briefly. Okay. Yes. Yeah. So this is not going to be on tomorrow's test, but this will be on the final. And I just want to make sure that before we leave for break, we have covered everything that we need to cover. And then those first 2 days we come back from break, we can ask, we got, 2 50-minute blocks that you can ask any question that you want to about the final, anything about what we've covered so far throughout the year. Just kind of a question that you see a lot of times with this. It says, this lady, Cheryl, makes payments of $500 per quarter into a retirement fund. Okay, so maybe a 401k, a Roth IRA, something like that. Okay, it earns 6% compounded quarterly for 25 years. What's the value of the annuity after 25 years? Okay, you also see questions that deal with like winning the lottery, how the lottery pays out a lump sum, or it'll pay out like yearly or monthly payments, right? Okay. Those monthly payments that are paid out to you or yearly payments that are paid out to you are kind of worked out with an annuity formula like this. Okay. But what happened, this is different than our compound continuously and compound quarterly or monthly or anything like that, because those you start with a principal, and that's the only investment that you make. Okay. So you put $10,000 in, and then you're hands off, and you don't touch it again. You don't add to it. You don't remove from it. Does that make sense? Okay. With these, you're doing a monthly contribution or a weekly contribution or something like that. Okay. This lady's doing quarterly, so she's doing it every 3 months. Okay. A lot of retirement plans are set up to do monthly, or you can do like bi-weekly. But a lot of, like an Edward Jones, they will buy stocks or bonds or whatever you're investing in. They buy them once a month. Okay, so a lot of times that's what you do. Okay, when we do an annuity, I'll just write the formula here for you. We could go through, saving time. We can go through how this formula is generated, but I'm not going to. I'm just going to tell you that an annuity. Okay, the amount after some time is found by taking R. Okay, R is what we refer to as your periodic rent. Okay, meaning that's just the amount that we're going to put in or contribute to this fund every quarter or every month or whatever. Okay, so that's the repetitive or repeated investment. Okay. Okay, so we take that, and now we're going to multiply that by 1 plus I. Just kind of write down these. Write down our variables here. I, okay, it's not your pure interest rate. So in this case, I is not 6. Okay? This is the interest rate per compound. Okay? Meaning you take interest rate and divide by how many times you're going to compound per year. We're going to raise that to the n. N is number of compounds for duration or the life of the annuity. We'll subtract 1 from that, and then we divide by that same I again. Okay? And that will give you an idea of, okay, if I keep making payments making basically, 4 payments every single year for 25 years of $500, and I'm earning interest rate off of each of those investments and the old investments that are already in there. Hopefully you realize that you're going to increase much faster in regards to your amount in your account because you are contributing on top of all the interest that you're making. Does that make sense? Okay. So if I start with $500 as my first payment, okay, now a lot of times when you set up a Roth IRA, okay, so you're setting up a retirement fund, those things have kind of like an initial investment requirement. I think right now a Roth, you have to start with an initial deposit of $5,000, okay? Because you have, because of stocks and mutual funds and stuff like that, there are limits that say you can't just go into a mutual fund and contribute and buy $30 worth of a fund out of it, okay? Some mutual funds say you have to have like a $500 starting investment to be part of it. Does that make sense? To own those stocks, okay? You guys know what like mutual funds are? Okay, so you guys know what stocks are, right? Okay, so a mutual fund is, and somebody, some governing body kind of watches over it and manages it, but it's simply that it's taking a diverse set of stocks from different companies and putting them all together at once and saying, okay, now if I go put $500 into that mutual fund, I'm buying maybe ownership of maybe 30 different businesses. Does that make sense? Okay, and their mutual funds are kind of separated in to like you got your international, you got your domestic, you got like your tech stuff, you got medical mutual funds and stuff like that. Does that make sense? So they're kind of categorized so you can say, well, I want all my money in like international tech. In doing that, you don't take on as a investor, you don't take on as much risk. Does that make sense? If I put all my money in Samsung, okay, and Samsung has, they're trying to avoid tariffs, China tariffs right now, and they go to Canada and get arrested. If you looked at their stock lately, it's dropped a lot, right? Okay. Well, if I put all my money into that, I just lost out a lot, okay? But if I put my money into a mutual fund that incorporates Samsung, then only maybe a certain percentage of what I've invested is in that business, then I don't take on that much risk. Does that make sense? Now, mutual funds allow you to be more diversified, which ultimately allows you to kind of minimize your risk in when a company has a bad month or just a bad quarter or something like that. At the same time, if it minimizes my risk, it also minimizes my potential gains, right? Okay, if I don't put all my money in one of those. Are you picking your nose, man? It's gross.
Yeah, can I have to the bathroom?
Yeah. So if I'm doing my investing to minimize risk, I also minimize potential gains. I don't put all my money in Samsung, and Samsung has a great quarter. I don't earn as much from that as I could have. Okay, so those are all things that, like, if you're interested in being a financial advisor, that they kind of hopefully shed light on for you. But here we've got, so our periodic rent is 500. Okay, it's always going to be 1 plus now I. I, like I said, it's interest rate divided by the number of times you're going to compound it. So how many times am I compounding? Quarterly, right? So this number here is actually 0.06 divided by 4. If I take 0.06 divided by 4, what do I get? Okay, what's 60 divided by 4? 15, right? So 0.06 divided by 4 is 0.015. Okay? Now, N is the number of compounds for the duration of the annuity. The annuity is going for 25 years, right? You're compounding it quarterly. How many total compounds is that? 100. We subtract 1. Okay? This is over then I, which is that 0.015. Okay? Now, just be careful, because when we have this form, this R out here is out in front. Obviously, you can put that up top, right? If you wanted to. If I put it up top, there is a difference up top, right? So I would need parentheses there. So if you're going to put 500 up top when you take your calculator, absolutely do that. But you can't just put one set of parentheses. Does that make sense? You need 2 sets of parentheses, because that 500 is needing to be distributed to a difference now. Okay? So now if I type that in on our calculator, we go 500, 1.015, raise that to the 100th, minus 1. Okay. So I need one more parenthesis. Gives me what I do. What parenthesis am I missing? Or what one do I have too many of? I have too many. Let's see here. Delete. Okay, so I didn't need the extra one. So I got that. And now I'm going to divide that by 0.015. I think this is the easiest thing to do. And I get that number right there. Okay? So after 25 years, with my contributions, along with the compounded interest, I now have $114,401.52, right? Just by making those, that initial deposit 500, and then continually making that every 3 months. Okay. There is a lot of stuff in finance, guys, that you can kind of look at certain formulas to deal with. Okay, what happens if I want to increase my payments every month, right? Okay, because you can do that. Okay. Now the government sometimes puts restrictions on those types of things. Like last year, my financial advisor told us that they were coming out with a law, and they did that. Kind of put a cap on Roth IRAs, saying that if I was only putting $250 in previously, then I can't ever, for the rest of my life, ever put more than $250 in that Roth IRA. If I wanted to put more in, I need to open another Roth IRA with another $5,000, and then I can start putting stuff in that as I want. Does that make sense? Okay. So they did that for like 6 months, and then the current administration said, nope, we're overhauling that. We're going to go back to the old thing, and now you can increase your investments if you like. Okay. Which is kind of I think screwy, but because it hurts some people because they open those extra Roth IRAs, right? Now, ultimately, in the end, they're going to be fine, but maybe they were strapped for $5,000 to open it. They wanted to open it, so they put in $5,000 out of their savings, right? Okay. And then 6 months later, they find out, well, I didn't really need to do that. I could just wait 6 months and been fine and keep adding larger contributions to my original one. You can merge those things. You can withdraw from them, but when you add to a Roth, this is the purpose of doing that. It's sheltered, meaning that it's pre-tax. Does that make sense? Okay. If I take out before I retire, that money that I take out, if I want to take out $10,000, it is taxed right there when I take it out, and I don't really take out $10,000. Does that make sense? So if I want to actually have $10,000 taken out and purchase something for $10,000, I got to do the work to figure out, okay, I really need to take out maybe $13,000 because it's going to tax off maybe 30%. Does that make sense? But when I retire, things are a little bit different. The rates are a little bit different than when I withdraw. And those are all things that I wish there was a math class in high school or in college. Obviously, there is in college if you go into that field. That just introduces you to how you deal with credit cards, how you deal with mortgages, how you deal with. Now, I know we got financial literacy and everything, but I think there's a lot of things that maybe we could do a little bit better and explain those things, because it is extremely terrifying when you go into. You're excited when you go into a bank and you're buying a home and they give you the numbers and say, well, after 30 years, you're going to spend $500,000 on this home. That's scary, okay? It's scary when you go buy a car. It's scary when you go invest and say, okay, it's just that unknown, okay? 30 years from now, am I going to be able to retire, okay? And if you're informed about that stuff a little bit sooner, would be very, very beneficial. Now, why don't we do those things? No, because